Hi, today we're going to be going over Chapter 1, Section 1, Part A of Modeling and Equation Solving. So this section refers to the PDF, Regression on the TI Inspire Simplified, which you can find in our class drive folder, which you can get to from our Google Classroom. Once you're in Google Drive, it is in the TI Inspire Instructions folder. And that is just if you're not too comfortable or familiar with using your TI Inspire to do something like what you're going to see down here, making scatter plots, plotting graphs, doing computations. There's a lot of good how-to stuff in there, which I'm just going to take for granted in this video. So let's get started. A numerical model, numerical, numbers, model. Something that's going to represent something, right? A numerical model analyzes numbers or data to understand some situation or phenomenon. So consider this table right over here that describes the percentage of prisoners in the United States that are female. So female percentage of U.S. prison population. When we have two variables like this, and one of the variables has really large numbers, it's kind of nice to just go ahead and start off by zeroing something out. So instead of starting with 1980 and using that in our computations, let's just call that year 0. So let x equal the number of years after 1980. So 0 years after 1980 is 1980, right? And then we can quickly simplify and look at and have smaller x values to work with. And go ahead and let y be the percentages of prisoners who are female. So this 3.9 means 3.9% of all of the U.S. prisoners in 1980 were female. So for instructions on how to make a scatter plot for this data, x and y, again, refer to that PDF, but here's what it looks like, right? So here I've got years, really I should say years since 1980, and this is the percent female. All right, and here's our beautiful scatter plot. So to see if there's a linear pattern to the data, let's go ahead and write the equation of the line that contains the extreme points 0, 3.9 and 37. So if I were going to draw a line between these 2 points, it's not perfectly straight, but you get the idea. What would the equation of that line be? What's m? M is our slope, right? B is the y-intercept. So what would those be? If you said or wrote down, well, it's going to be 7.0 minus 3.9 because it's the change in y divided by the change in x. You're absolutely right. So 3.1 over 30, which is going to give you a really long decimal. It's approximately 0.103, blah, 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 blah. Or keep it in exact form and just write it as 31 over 300. Or, I mean, technically 3.1 over 30, but that just looks prettier. B, your y-intercept is 3.9, right? Which, yes, you could technically write as 39 over 100, but for some reason, I'm okay with that. But with slopes, I like integer over integer. So you're getting to see some of my nuance. So the equation of this line, which I'm going to call f of x, is 31 over 300x plus 3.9. And I'm going to put that x in the numerator just so that we're clear that it is in the numerator, not the denominator. All right, so draw this line on the scatter plot to see how it fits the data. So, do you think this is a good fit? Do you think this line is representative of all the data points we've got here? Yeah, I mean, it doesn't seem like it is very close to these lines. It looks like it might have similar slope to like a line through these guys, but it's not very close. So this is the point of regression. Right? You can also generate a linear regression equation that will be a better linear model. And I'm not going to go into the mathematics of how you compute that. That's kind of more of a statistics topic. But the regression line is often called the line of best fit. And here you can see, right, again, use the above mentioned PDF for instructions on doing this on your calculator yourself. But you can see this is the equation of the regression line, the line of best fit. And if I scroll down just a little bit more, we can see, yeah, comparatively, the regression line, not the red line, but the red line is the one that we computed. But the regression line actually fits the data a little bit better. The data points are much closer. All of them collectively are much closer to the regression line than the line that we drew. So this is us comparing the two lines on the same graph. So use the scatter plot and the linear equations to answer the following questions. So if you're watching this, go ahead and pause the video and see if you can answer questions 1 through 5 right now on your own. All right, so assuming you have paused, let's go over. So what has been the overall trend of the percent of prisoners who are female? Well, overall, there appears to be a modest 0.1% increase each year. And where did that 0.1 come from? That was our slope, right? That was the slope of our, both of them, right? Because 31 over 300 is approximately 0. I think, yeah, I wrote it 0.103, blah, 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 I think, but about 0.1, right? So how do M and B of the linear models describe this trend? Well, the slope M indicates that increase every year. Because M is positive, that indicates a positive increase. And the y-intercept B, it doesn't really indicate the trend of going up, but it indicates the initial value in our table, which for us was the 1980 percentage. So if this trend continues, what will be the percentage in 2020, 2050, or 2100? Maybe that's how we'll say it. I don't think I'll be alive then, but, right? If you use our first line, right, the red line, F of 40, you're going to get 8. So in 2020, 8% of women. In 2050, 11.1%. In 2100, 16.3. If you use the regression line, F sub 1, then you're going to get slightly different percentages. So which one is the right one? Well, the answer is they're just predictions. There's no way to know with 100% certainty if any of these are going to be right. These are just our best guesses. And of the two, the regression line is probably the better guess. But if you didn't have this, your red line answers are good enough, right? If this trend continues, when will half the prison population be women? Well, that means 50%. When is my function going to equal 50%? So you can solve this algebraically, right? X, if you use our red line, our original equation, X is approximately 446. So add that to the original year date of 1980, that would be in the year 2427. Half of all of our prisons will be filled with women. Or, I guess rather, half of the prisons in the US will be filled with women. Because right now they don't mix genders in prisons, I'm pretty sure. But using our regression line, it would happen sooner. So, the last question, is this a good long-range model for the percentage? Probably not. First of all, regression lines or any predictive model usually is only good in the near future. The further away in the future you are looking for predictions, the less effective, the less accurate your models are going to be. And in this model particularly, because it's linear, eventually this model is going to produce percentages that are greater than 100%, and that's just nonsensical. That's when it's completely ineffective. All right, so that's numerical models. What about algebraic models? Well, let me switch over. Algebraic model uses formulas to relate variable quantities associated with the phenomenon being studied. So the linear equations above were linear algebraic models for the percentage of prisoners who are female. But now, how can we tell from the data, from those numbers, if the model really is linear or maybe if it's quadratic? Well, we do that by examining how the values of y change relative to how the values of x change, and specifically if x is changing by a constant amount. So let's start with what I hope you know, is a linear equation and a quadratic equation. And let's look at those tables and see how they change. So for time's sake, I'm just going to go ahead and look at our solutions and let's compare. So our linear model, right, when x is 0, you get 4, 7, 10, 13, 16, 19. Right? For our quadratic model, we have when x is 0, f of 2 is 1. Plug in 1, we get 4, 9, 16, 25, 36. Now, here's what makes the difference. These are each increasing by 1. So x is changing by a constant in both of these situations. But how is y changing? Well, in our linear model, if our data truly is linear, then these changes will also be constant, right? As x changes by a constant, and by the same constant every time, y will change, or f of 1 will change by the same constant. So f1 values increase by, whoa, that's a typo, not 2, 3. They increase by 3 when x increases by 1, right? This is what makes it linear, right? Rise over run constantly. But in this case, my y values are increasing, but not by a constant, not by the same thing every time. In fact, the numbers that it is increasing by are themselves increasing by a constant number, right? 3, 5, 7, 9, 11, that is a linearly increasing sequence of numbers because these numbers are increasing by a constant. So the increases of F2 are linear. F2 itself is not linear, but its increases are linear, right? If you happen to say, oh, 1, 4, 9, 16, 25, 36, those are all perfect squares, so it has to be quadratic, right? That's not always going to necessarily be the values that you see. And we'll see that in our last example here. But moral of the story, increases in F1 are constant, while increases in F2 are increasing, and they're increasing in a linear way. So let's look at our last function here, right? Suppose we use a square root function. F of 3 is the square root of x minus 2. So here's our table of values, and in this case, we're picking specific x values that give us really nice y values, right? If I plug in 3, 3 minus 2 is 1. If I plug in 6, 6 minus 2 is 4. Rad 4 is 2. And so here, my x values are increasing by 3, 5, 7, 9, 11, while F3, the y values, are increasing by a constant. So in this case, the increases in x are linear. And here, the pattern of increases for F2, what we just saw in F3, they're reversed. So how are the patterns of change in the square root function related to the patterns of change in our quadratic? Well, clearly, right? It's because quadratic functions and square root functions are inverses of each other, right? The shapes of their graphs are going to be reflections of each other. So let's practice graphing quickly. Let's graph those 3 functions that we just saw. So go ahead and sketch and use at least 3 of the values that you generated. F1, F2, and then F3 down here at the bottom. So go ahead. I've got scales. I've got axes already there. Go ahead and take a quick look. So pause. See if you can sketch these on your own. All right, welcome back. And in the last minute or two. All right, so F1, 3x plus 4, 1, 2, 3. Those were the 3 points from our graph. And you'll see again, rise of 3, run of 1, rise of 3, run of 1. So I've just got the rise here. For our quadratic, right, it's interesting. From our vertex, which wasn't technically in our table of plots, but it's there, right? This guy factors nicely into x plus 1 quantity squared. So from our vertex, you go over 1, up 1, go over 1, up 3, go over 1, up 5, and you've got that pattern for your quadratic. And then similarly, for a square root function, over 1, up 1, over 3, up 1, over 5, up 1, then you'd go over 7 and up 1. And that is our graph. So go ahead and take a few minutes and look at these additional notes and practices. Try example 1 and example